Yeah, kia ora koutou, everyone. I'm Nisha. I'm the training lead at Nessie. I'll be chairing this session on workflows today. We have four very interesting talks lined up this hour, starting with two full-length presentations, followed by two demos. Please feel free to pop in any questions or comments that you might have in the meantime to into the live Q&A chat box. You can access this by clicking on the box to the right of your screen. So let's quickly begin by introducing our first speaker. Um, it is Alexander Pletzer. He's from Nessie, and he'll take us through his talk titled "Are Workflows the Next Big Thing in Scientific Computing?" Over to you, Alex.
Oh, okay, thank you, Nisha. So this is about whether workflows, would be the next big thing in scientific computing. This is something that, of course, does not happen, every year. We had a number of great breakthroughs in the past few years. GPU computing being one of them. We had machine learning and object-oriented programming maybe in the past. This is really more a question than an answer at this point. But I had some interesting discussion with my colleagues at Nessie, including also including Hilary Oliver, who's the main author of the Silk workflow engine. So here the motivation why I'm saying that is that the clock frequency of CPUs and cores in particular has not increased in the past 20 years or so. So the cores are not getting any faster. We just have more cores. And this is what this plot attempts to show on the right-hand side. Hence, when it comes to actually doing more computation, we have a number of avenues to achieve this goal. And one of them is to migrate the code and run on the GPU. That's the graphical processing unit. And this has shown to be extremely advantageous in some code, but involves a lot of work in terms of reprogramming models and codes and so forth. Another one would be using OpenMP, or you could use the message passing interface. But all these methods actually require a rewrite of the code to a very large degree. Right? What I'm going to talk today about is something that will allow you to scale up in terms of complexity of this kinds of science that you're conducting, but actually without rewriting your code. And that's where workflows come in nicely. So if you have, a workflow is essentially just a sequence of jobs that you have to run, and they have to be coordinated in some ways. Now, we understand that you can do that manually, and that's probably okay if you have just a few jobs to submit. Or you could write a bash script, and Callum, who is going to talk later, is going to talk about that as being a possible solution. We also have Slurm job arrays and tasks, which we have used in the past during our consultancy work for Nessie by working with scientists. But today what I'm going to talk about is using a workflow management system. And here you have the choice between a few, some of them which I've been mildly familiar with, like SnakeMake. I've also used Galaxy in the past, but more recently I sort of became acquainted with Silk, which I think is a very nice option, which is installed on Nessie platforms. So sometimes the question arises, when should I use a workflow management? And it's a bit like a rock band. If you have 4 players playing guitar, maybe you don't need a conductor. But once you have enough musicians, and here the analogy would be that each musician or each singer here in this choir would be a job to submit, then maybe you're going to benefit from a conductor. So this is something that there's an idea by Callum, who's going to talk later, but so he's going to reiterate these things. But I think it's important to realize that a workflow is made of basic building blocks, like the atoms of matter. And we can think of a few of these building blocks being, sequential execution. So you have a task A that has to be followed by B and C and D. Or you could also have concurrent execution, which is really nice because A, B, C, and D can actually execute simultaneously. Another interesting pattern is the scatter pattern, where maybe you start to prepare some data and then you run 3 models, B, C, and D, or you might also do some gather pattern, which would be, running A, B, C, and then gathering the results and maybe running some statistics. Now, keep in mind that when I write A, B, C here for the gather pattern here, I'm not actually very precise about what I'm saying. Does that mean actually that A, B, and C have to run, or could it mean that A or B or C should run, or maybe that A and B or C should run? And that's an interesting discussion that we can pursue after that presentation. Another interesting pattern is the cycling pattern. So you have a little bit that a basic a building block of that workflow, but now you're going to iterate, or you're going to repeat that building block over and over again. And potentially you could do that for to infinity. So you could just have a workflow that runs forever. And there are cases, particularly in paleoclimate simulations or other contexts, where it is desirable to run a code for a very, very, very long time. I actually worked at one place in the US where they had to basically stop a code, change the machine, recompile the code, and continue essentially the simulation across 2 completely different platforms. And so we could even imagine that some of these workflows might live longer than the life expectancy of a platform, and possibly even a human over time. Now, here is another interesting one, which is the graph branching pattern, which was suggested to me by Hilary. Apparently, it's a fairly common pattern that is used by the Silk workflow engine, and it involves a model that runs, but sometimes it fails, right? And so you have 2 outcomes. You have success, which is sort of that green arrow, or you have failure, which is that red arrow. And if it fails, might be the time step was too large, or for some other reasons, then maybe you want to diagnose that and rerun that model, maybe with slightly different input data or different input parameter, and then finally do the post-processing. So you don't actually know exactly in which direction, which branch you're going to run until runtime. And I believe that not all workflow management systems will allow that, because some, like SnakeMake, they go backwards. So they're thinking in terms of, what are the results of post-processing, post-proc, and then trying to figure out what models or what tasks should be run. But you don't know. You have to sort of start from the top and go down. So another one that was suggested to us last week, there was a meeting, the Antarctic Science Platform, and we had a discussion with a scientist, and that scientist wants to run a model for a very long time, months in a row. Now, needless to say that at NESI, we do not allow typically people to run for that length of time, and that person would actually be stuck in the queue for a very, very long time. What needs to happen here is that one runs a model, maybe for a day, writes a restart file, and then starts again another day and another day and another day. Now, this is very tedious because you have to do that every day, including on the weekend, and maybe you want to restart the model in the middle of the night. Wouldn't it be nice to automate such a workflow, right? And so that's the restart pattern. So essentially, we prepare the data, we run, and maybe the run crashes because we exceeded the time, the wall clock time, so it fails. So it runs another preparation step, runs the model, fails, and so forth. But in the meantime, it sort of might actually write some files which I've not represented here. And so eventually, after 30 attempts or so, then the workflow actually succeeds. So as part of the consultancy team at NESI, we have encountered workflows over and over again, but they've been used in different ways. We had a presentation this morning by Alexandra Pavlik, who worked with a researcher called Jesse Pebble, and we split essentially their computation into the submission of many workflows. We actually currently also working with another researcher, and I don't have the data here or the plots to show, who's an hydrologist at NIWA Hamilton, and we did exactly the same. We applied exactly the same gather. It's a gather pattern. Talking to my colleague Maxime Rio, one of the most common pattern, and that's the case for these two plots here, is to use when you're doing machine learning. Essentially, you want to compare the accuracy and performance of different machine learning models. And how do you do that? Well, you run them in parallel, and then you have that gather operations that combines essentially all these results and analyzes and finds out which model actually performed best for a particular situation. And that was also the case here of a machine learning project last year that looked at car crashes with Nick Young and again Maxime Rio. Finally, in the lower right here, that was a very nice example of how workflow accelerated essentially the research of the scientists. What the scientist here was doing, that was Johnny Williams at NIWA, he was analyzing climate data, and it took about a week to actually get the results of increase of temperature, increase of CO2, precipitation, and so forth globally over the Earth. They had to plow through tons of data. And these little bars here, this is a histogram that shows the execution time in seconds of each of some of these tasks. Varies enormously. So you have the seconds on the x-axis. And so some tasks are very, very quick and some are very long. And one of the really nice things of workflow management systems is that they have built-in load balancing. So essentially you don't have to worry about load balancing at all, like you would in an NPI code. So here I'm ready to summarize the main ingredients of this presentation. Is A, you don't need to know how to write parallel programs to take advantage of workflow management systems. B, workflow management systems lead to the most efficient use of resources, because instead of submitting, a monster a Slurm script which requires 10,000 cores, what you could do is you could just submit little bits, and if the machine is not very loaded, all these little tasks could potentially run in parallel if it's a gather or scatter, a concurrent pattern. But if not, at least you get some tasks running while the rest may be waiting in the queue, but it pushes essentially the stream of operations would be much more continuous. The workflow management systems are also typically lazy, so they're not going to run things that you have already run. They remember essentially what's been done, whether you have already produced your output files, as in the case of SnakeMate, or whether in the case of Silk, the system itself will remember which tasks have been successfully run or not. And so it's very sort of potentially attractive way to add multi-physics. If you have different codes that simulate maybe the ocean, ice, and land, and vegetation, and biology, and so forth. And these might be developed in completely different labs. They don't have a common API. So how do you couple that? Well, a workflow is one way. Something that is very important, and Callum reminded me, was reproducibility. If you manually submit 50 Slurm jobs, you may not actually remember exactly in which order you submitted them, what in which circumstances, and so forth. So if an issue arises, then you might not be able to find that out so quickly. So I'm done, and would I encourage you to just stay in that particular session. I think there are going to be a lot of other very interesting talks. Thank you.
Thank you so much, Alex, for your much needed insight into the world of workflows. Do we have any questions from the audience? Any questions, comments, thoughts? I mean, while we wait, Alex, one of the things that I have been thinking about was there are so many workflows out there, right? And what do you think would be 2 or 3 pointers that you would suggest to someone who's trying to figure out the best workflow for their research?
Yeah, that's a very, very good question, Nisha. Thank you. I think the one of the myth I want to dispel is that workflows have to be really complicated to use. And what I've learned, at least with Silk, and I struggle a little bit more with SnakeMake personally, but that's your mileage may vary. That how easy really it is to get started. The bar of entry is very, very low, and so we have documentation. I don't think we're pushing for a particular workflow management system. I think it again, it's going to depend on the applications, depends on what people are using in their community. SnakeMake was developed in the context of bioinformatics, but it can be used elsewhere. As Maxime showed, it could be widely used in machine learning as well. But the same is true of Silk. Silk was developed in the context of weather forecasting, but it can be used in other areas. I personally have, my favorite would be Silk at this point because you tell what the tasks are, and you don't even have to define the tasks. You define the graph, and you start working from the graph and then implement the task. And I don't think you can do that with SnakeMake at this point.
Thanks, Alex. We've got a couple of quick questions from, I think, Lucas. Lucas was the first one. So you mentioned a couple of workflow systems. What workflow languages are they using, and which one do you think is the best one in your opinion?
Yeah, so that's a little bit related to the other questions, but and I don't know to what extent these workflow management systems use a common language. The two that I know are SnakeMake and Silk at this point, with some experience with Galaxy in the past. In the slides, if I go back, I basically wrote down the equivalent Silk expressions for some of these graphs, and you will find that it's very intuitive. So I don't know if they are standard at this point. We might have to ask Hilary, who's going to run a live demo later. But really good question. Thank you.
And just 2 quick questions, Alex. We've got only 2 more minutes, so. Murray says, what would be some key things to look out for to point towards shifting into a workflow system? And Wolfgang,
automation.
Sorry, Alex, yeah.
Yeah, so automation. So if you feel like you're doing something really, really boring, and you want to delegate, that boring stuff to something that can manage that for you. You can also scale up. That's one thing. Talking to the scientists and other users, it's just amazing to see that you start a discussion and they don't know why they would use a workflow, and after 10 minutes of discussion, they suddenly want to run 1,000 tasks at the same time. That's what I see. Yeah.
And very quickly, Wolfgang says, which workflow management tool would you recommend for beginners? I think that ties in with the first couple of questions, but yeah.
Very, very shortly, I think at this point, Silk is my favorite.
Thank you, Alex. Okay, quickly moving on to our second speaker of the day, Callum. Callum McDonald-Wally is from NESI, and he would be taking us through very quickly a talk titled Building High-Performance Computing Workflows, Feat, Bash, and Slurm.
Hello. So tēnā koutou katoa ko Callum aho no Nesi aho. So I'm Callum, and I'm going to be building a little bit on what Alex has just said about workflows. So I'm going to be talking about specifically high-performance computing workflows, and not workflow engines, just the tools you could use to build your own workflow. The slides I've got at the moment are based on a webinar/workshop I plan to be running at some point. So keep an eye out in the NESI newsletter if you're interested in reading that or attending that. the materials on GitHub. So a sort of longer version of this is on GitHub if you're interested in that. So starting off with the laziest possible way you can start off any talk with some Wikipedia definitions, but it is important to get the concepts across that a workflow is not a piece of software, it's not a language. A workflow is just a structured approach to dealing with data. So a workflow can be entirely in your head. A workflow could be something you've written on the back of a napkin. It's just a structured approach to repeating the same job over and over again. A pipeline is a workflow where, it's kind of the trendy word at the moment, is a workflow where the output of the first thing goes straight into the input of the second thing. So it's just a type of workflow that is sequential in nature. And workflow management systems is a piece of software that's been written specifically to help you organize a workflow. So that's normally when people are talking about a workflow, they're talking about a specific workflow management system. But I'm just going to be talking about the basics of automating a workflow that you built yourself. So it's important to have, you need to have a workflow no matter what jobs you're doing. It's just a matter of what tools you're using to build it. Oops, I'm just going to skip past that patterns because Alex kind of covered that. So when considering what you're going to make your workflow with, you need to be considering, how complex is this workflow? Is it just am I just reading a file, modifying some data and then writing it again, or is this a long-running, multi-branching, conditional, multiple fail states, etc., etc.? If so, I might want to consider using a full-blown workflow engine. Whereas that previous example of just modifying some lines in a file, which is a workflow if you're doing multiple steps, you could probably just have that as a command line. It's just a single line command. So it's important to have a think about, how many times you'll be doing this task. If you'll just be doing it a couple of times, then it's probably not worth learning a workflow language or even necessarily writing a script for it. But if this is something you'll be doing a lot, then you'll definitely want to be investing some time in making sure that you have suitable workflow automation set up. But also don't forget that other people have probably already done what you're doing, so you should check that out first. Save yourself some time. So I want to emphasize the fact that a workflow is a structure, and the most important part of it is, and something that a workflow engine can help you with a little bit, but it's mostly something you have to do yourself, which is just think about what your data is doing. So think about where your data is going to come from, where it's going to be when you're processing it, where it's going to go when you're finished processing it, having a file structure set up that makes organizing that easier. Joanna's talk this morning was really, really great. I was just sort of just going, yes, say it again. Like that was, go back and watch that if when the recordings come out. So having your data with a consistent naming scheme and a well thought out file structure is pretty important to having a good repeatable workflow. When I'm helping people with sort of workflow related problems, I find that generally the majority of my time is spent kind of figuring this out. So trying to figure out, well, where is your data? Where is it going? What are the steps in between? So if you have that sorted out already, the actual technical implementation or fixes is a smaller part of the problem. Now, so I'm going to be talking mainly about the HPC, the NESI HPC, which is a Linux environment. You're probably going to be, if you're doing any sort of high performance computing, it's probably going to be in a Linux environment, to be honest. Now, Unix processors were built around the idea of standardized data streams. So all processes have a standard input stream. You might see the words stdin. They have a standard output stream, or stdout. They also have a standard error, but we'll kind of ignore that for now. The streams they can be binary, but normally just text. So the great thing about these is you can use a pipe to connect one process to another, and a pipe in this case is literally that horizontal pipe symbol. So what you're doing there is you're just joining the output of one command or one process into the standard input of the next process, and you can chain that together as much as you like. So the examples there is someone WC, so reading from a file, reading the number of lines in a file, sorting it, and then heading it. That is technically a workflow. You're doing multiple commands and you've got them lined up one after another. So this is what I mean when I say a single line workflow. So your workflow is just a series of commands that you've joined together on one command in the command line. So you can actually do some more advanced stuff than you might think. You can do you can split your input streams into multiple directions using T. You can do conditional logic. So do X thing if the previous previous task failed. Do Y thing if it succeeded. You can build some pretty advanced workflows in a single line. You shouldn't. That's not very unreadable. There is a certain satisfaction to building a really long, complicated single line command, but it's definitely not best practice. So anything more than a couple of processes linked together, you're probably going to want to write a script. So a script is in the most basic sense just a series of single command line calls one after another. So starting from the top, it will execute sequentially the first line, then the second line, then the third line. I'm talking about Bash specifically here, but I mean, it can be any language really. It's just Bash is particularly easy in an HPC environment. A trick, the -e flag there is used to determine the failing behavior. So if -e is there, the whole pipeline will stop if one step fails. You can also quite easily do asynchronous stuff. So all you need to do to make a task run in the background is use a little AND symbol. So that example there will run those 3 tasks, wait until they all finish, and then run the next task. So again, examples of quite simple ways of making these workflows. Now, unfortunately, we're on an HPC platform. So if you just put all of your individual computational tasks one after another, you might end up in a situation where where this is a quite long running bioinformatics pipeline, and you can see the resource usage of CPUs and memory, and it's very variable. So as we can see, huge amount of wasted resources here if we just have one big allocation block. What we really would like to do is have each step of the job have its own tailored Slurm job, which run one after another. Now, that looks like a lot of work. I mean, this is the kind of job where you would probably be wanting to use a workflow manager. But, for the sake of this demonstration, you don't want to be just running the first bit, waiting for it to finish, and then running the next bit. Luckily, Slurm has a thing called job dependencies. So, this is an example of what not to do. Just submitting the next script at the end of the first script. You could do that, that's perfectly fine, but luckily Slurm provides us with these dependencies, so pretty much it gives you the ability to give a condition under which your job will start. So you can say, only start this job if the first job succeeded, ran to conclusion. So a nice little trick you can do is in your main script, if you submit the script that comes afterwards using its Slurm ID as a dependency, then that will give the job the entire time that your first job is running to queue up. So it should start immediately rather than just throwing it into the queue when your job finishes. So you can also, there's a nice snippet to get the job ID of a job you've just submitted. So this example here submits 3 jobs, except the second job doesn't run until the first job is finished. With these snippets and stuff, it's not worth trying to remember it. Just copy them from somewhere, the online workshop probably. The last thing I'm going to mention real quick is how you do the job-based parallelism, which is what Alex was talking about. Is sort of a really important and useful part about having a structured workflow is using job level parallelism. So that means you're getting your parallel performance by just running lots and lots and lots of jobs at the same time. It's also probably a pretty central part of a scatter-gather workflow. So splitting up your job into lots of little things and then collecting them afterwards. So Slurm array jobs are a way of, with one script, running as many of that job as you'd like. So I can provide one script, I give the argument 1 to 10, that job will run 10 times. There's some fantastic things you can do with job array jobs. It's not something. It's the reason why you would use an array over just a for loop is pretty much you'll be banned from the platform if you submit jobs in a for loop. Pretty much. Well, if you're submitting thousands of them, it takes a bit of a toll on the cluster, as well as being just difficult to manage. Again, it's something you want to look at examples for, but just good to know they exist. Last thing I'm just going to mention really briefly is scrontab, which if you're familiar with crontabs are just a way of running repeatable jobs. So you can schedule a time for your job to run. scrontab is the Slurm implementation of crontab. So you can give it a script and it will try and run that script, say, every morning or every day at 5 o'clock or every hour. I don't know, that's probably a bit too frequent. But yeah, so my aim here was just to sort of bring up, mention some of the tools you can use to build simple to moderate complex pipelines. Now, what's the time? That's all I've got. Questions?
Awesome. Thank you so much, Cal, for taking us through your brilliant presentation. Do we have any comments or questions? Any thoughts from anybody? Yeah, while we're waiting, Cal, I think I'll ask the same question that I asked Alex, which was that if you really had to choose, what would you suggest to somebody who's
Oh, I'll post the link to the workshop I'm making.
Yeah, we've got questions coming in. Alina,
Plan on putting a lot more examples in the future.
Cal, can you hear me? I don't know if you can. Can you hear me? We've got a couple of questions. Alina's asking, very useful Nessie workshop to follow. So I think Cal is going to send us the link soon.
Do any of these aspects change when using GPUs?
Yeah.
Only the commands you'd be using to schedule things. GPUs are, yeah, quite likely a thing you would use in a workflow, because you'll often have stuff that doesn't need a GPU, and you don't want to be running that in an allocation with a GPU, because that's unnecessarily expensive. Wait, I'll just finish answering these questions. But the only thing that would change is how you're requesting resources, pretty much. There's also a lot of stuff on the Nessie documentation around dependent jobs and job arrays. So you could find some examples there. You can run any, so when I was talking about a process, I just mean a kind of, a black box of the thing has an input, the thing has an output, you want to join it to something else. So your intermediary step there could be a Python script. Python also uses standard inputs and outputs, so you can write your script in a way where it could be easily integrated into pipes. Also, more broadly speaking, a workflow doesn't have to necessarily use Unix standard ins and outs. It's just a ordered way of approaching a problem. So your pipeline block could start off by reading a file from a specified location.
I think that's it for questions. Thanks, Callum. Let's move on to the next presentation and the first demo of this session. Hillary, our next session will be, oh, sorry about the background noise. Next, we have Dr. Hillary Oliver from NIWA, introducing us to Silk 8 workflow orchestration on Nessie. Whenever you're ready, Hillary.
Okay, thank you. I'm going to assume you can all hear me. Otherwise, speak up quickly. Right, so yes, I have a demo. Demos have been to 10 minutes or less because of demand, which is great, and on slots in the ROC conference. So I'm going to crack onto it, and we'll see how far we can get. So first thing is, I've got about 3 slides before I launch into the demo. Silk 8 is essentially a brand new system, the result of a 4-year re-engineering effort by the team. You should check it out. It's much easier to use and more powerful than previous versions of Silk. To get more information, if you're interested later, go to our website, silk.org. You can see that Silk's used by some fairly big names around the world, that's some of them, and click on documentation and you'll get straight to our online documentation. Whoops. We also have a discourse forum for asking questions and interacting with others. There's some information on the Nessie support pages that's very new, and it's a Kiwi-led open source project on GitHub. If you want to get involved. Super easy to get started. It's already installed on Mahawika and Maui, and at home on a Linux VM, say, it'll run out of the box after installation from CondaForge. All right, so the use case I'm going to demo has come up recently as something of interest to machine learning people, and it's a bit out of Silk's normal sphere of use, so but it's an interesting and small one. So if you're interested in this, that's also up on GitHub, and you can it's documented and you can run it. So the use case is we've got some raw data of some kind. We want to clean it to some form needed by a model. Then we want to run in different model configurations on that clean data, and we want to compare the results of the end models and report the results, the comparison. And then the idea is, sometime later, you might add some new model configurations and run the whole workflow again. The raw input data does not need to be reprocessed. The old models don't need to be rerun, but the new ones should run. And the comparison and reporting jobs should run again to include the new results. Okay, now I'll show you how to do that sort of thing in Silk. Let me just switch to my terminal. So this sort of workflow is basically replicating the kind of thing Snakemake does, which Alex mentioned, sort of working backwards from file outputs or output files to see when you run the workflow again, does the outputs from this step need to be regenerated or not, and you work backwards to infer the task graph of everything you need to run. Silk is natively dependency driven. It doesn't, you define what tasks are in the graph and when and how they depend on each other, and the scheduler makes them run if their dependencies are satisfied, without checking whether output files need updating. But the dependencies in Silk can represent anything, not just files, different task states, not even files at all, and we can do more complex things like conditional triggering and alternate graph branching, and cycling systems that continue forever, in which case there are no final outputs to work back from. So anyway, here's how to emulate that sort of thing in Silk. I've got a little source directory here. Have a look at it. In it, I've got a bin directory with some executables. Flow.silk, that's my workflow definition. I'll show you in a second. I've got a Python module and a live Python directory and some random other files. Let's look at the workflow definition. Someone asked about workflow languages before. Well, Silk uses a very straightforward config file format that ought to be fairly self-explanatory in simple cases. This example is actually a little beyond simple, but I think it's still pretty easy to understand once I explain it. However, if you need more advanced stuff, you can embed Python in this via via several forms of template processor, including the Ginger 2 template engine. There are other advanced things as well. So what I've done here is define a data directory where my data is. /data, and the data file prefix is COVID. And then I've defined parameters running from 1 to 10, and that's M. And here's my task graph. R1 means run once. Don't worry about what else you can do there for now. So we have our clean task, which cleans the data. After that, the M different models can all trigger at once. And after they're all finished, we can compare the results and report. This is a complete runnable workflow definition for as many models as you want, just using 10 as an example. And so this is in the scheduling section where you define your dependency graph. Down under the runtime section, we define each of the tasks, clean, model M, and the report task. And I'm defining input and output files for each in the job environment. And the root section here is that this is actually an inheritance hierarchy that tasks can inherit settings from, and this is saying all tasks are going to run this at runtime. It's going to start with an executable, which is actually a little Python program called skip, and if that succeeds, we're going to skip the executable that would normally generate these files. And if it doesn't succeed, that means we do need to regenerate the data, and we're going to run an executable that has the same name as the task name. Now, it doesn't have to be the same name as the task name. I'm just trying to make a as simple as possible demo here. If it's a model task with M on the end, we're stripping that off because I've got one executable in the bin directory called model. So that is the complete workflow definition. I'm going to try and run it for you. First thing I'll do is install. Let me just check the time. How am I doing? Okay, I'm not going to talk about the installation process, but let's just cut to the chase and say to run a Silk workflow, you install it from the source directory into a run directory, and that you can keep working on your source directory in new versions while other versions are running independently. So here I'm installing the workflow and I'm playing it, and then I'm starting up our terminal UI to view it. Over on this side, I'm going to watch my, 1 minute left, holy crap. 10 minutes is short. So this is our terminal UI, and I'm running this little workflow, which is generating output files. There's the clean task finished, generated. There's the job details, where it ran, what its job process ID was, and so forth. Now I'm running all the models, and same deal there. And on the right, you can see temporary files being generated as each task runs and generates its final outputs. So you can see here, each of the models is generating a model-specific output, and then the final report task is essentially collating all of those to generate the final outputs. Now, I'm going to run one more thing before I'm done. Let me just copy another slightly extended case into the source directory. There are only two differences here. The first thing is I've defined a queue so that I'm cranking up the number of models to 30, and I've just assigned them all to a queue that says a maximum of 4 of them can run at once. The graph is exactly the same, and just to inform you how you would run these tasks via Slurm on Nessie, that's how you do it. I'm actually running this on my laptop, so I'm going to comment those out. Let's install and run this. Now, so I've upped the number of models to 30. You're going to see that the original models 1 to 10 are not going to, they are going to determine that their outputs don't need regenerating, and they won't run again. And we're going to regenerate everything from, we're going to generate outputs for models 10 to 30, 11 to 30 in the output directory there. And you can see in our terminal UI, everything ticking over there. And the last thing I'll show you is back to my browser. You want to look where all of the outputs are going. You can look in the Silk Review web-based system to look at your job standard out and standard error, regeneration of output files needed for model 28, and it's told us which outputs it's generating. And finally, the Silk 8 web UI looks like this. Here's the running system. I can show as many different views of the workflow as I like. I can filter for different task states like running, submitted, preparing, failed, whatever. I can filter by name. On the left are all of my workflows. Demo/run3 is the one I'm just running now, and we're viewing that. You can drill down to job details here. That would show the Slurm job ID if it was a Slurm job, and the host it was running on, and so forth. You can click on these tasks to re-trigger them manually, kill them even on remote hosts, all sorts of cool stuff like that. And there are different kinds of views of the workflow that you can get as well, such as a table view there. And super fast demo. That's it. Any questions? Sorry if I went a little over time.
Thank you, Hilary. Any questions or comments? Please pop them in the live chat Q&A.
I guess I would say I don't expect you to come away from a 10-minute demo knowing how to do this yourself, but I like Alex said, for relatively small workflows, even like this one, which is actually running 30 models all at once, it's a pretty shallow learning curve, easy to get started, and but Silk has the power to scale up massively to complex stuff if you need it.
Yeah, and if you can't think of any questions right now for Hilary, please feel free to send it through to him. Oh, there's a question. Sorry to be a little slow. Is that last view available to any users?
We do seem to have a few coming in. Is the last view available to any users? Yes, this graphical user interface here is available to any users. If you have any trouble getting it going, depending on how you're accessing the Nessie machines, you're welcome to ask questions and we'll help you out. All right. Very nice. John says, do you mind being tied to this product? Well, I don't mind being tied to it because I invented it. some 10 years ago. Now it's not my own work anymore by a long shot. It's been worked on by a lot of other people too and improved beyond site. But I love using it and working on it. It's a fun project to work on, and it's pretty damn useful if you want to automate stuff. All right, Johnny Williams, when will support for Silk 7 be stopped? For many of us, the current functionality works fine. Well, I don't think the support for Silk 7 is going to be stopped. It's just that Silk 7 is written in Python 2, and administrators are not even going to want to install it on new machines for that reason. Basically, Python 2 doesn't get even security updates anymore. It's a dead soldier. So not only that, Silk 8 has many features that are much better than Silk 7, and you might be surprised to find out that they're really useful to you, even if you think Silk 7 is adequate. Finally, really cool, sorry to be a bit slow. Oh, that's the one we've already answered. All right. Okay, I think that's it for the questions. I'm not sure if we have Nisha or somebody who can...
I am here.
All right.
My internet dropped off and I'm back. Thank you so much, Hilary, for taking all the questions in my absence here. Thank you. So we have one more speaker, and that is Matt Bixley from Nessie. And he's going to take us through a quick demo on RStudio workflow in an HPC environment. Over to you, Matt.
Good morning, everybody. Matt, I work at Nessie. I'm part of the app support team, same as Callum. I work with the wider computational science team and things as well. This talk today kind of motivated based on discussions with a number of people who are in the audience. I can't see who's here at the moment, but Alexandra, when I first started working at Nessie, we had a discussion around R and RStudio and the interactivity, and how Nessie weren't doing a good job with interactive type work environments. And John has spoken about that. We've got HPC, we've got the Flexi HPC coming on board, and Nessie having to change the way we think about how people use an HPC environment, and not having to be so dogmatic on you must submit by Slurm, you must. So somewhat of an update on what's going on with RStudio and Nessie. A large number of our users access Nessie via Jupyter. Really nice and interactive, a Windows-styled navigation platform that people would be used to on their Windows machines. A terminal. We can run Python, or we can run MATLAB, notebooks, consoles, Jupyter notebooks in particular, and we can run RStudio. And recently, there have been large updates from mostly Callum and Maxime, run kind of a squeaky wheel and go, can we have this? Can we have this? And Callum and Maxime do all the work and behind the scenes and make RStudio nice and flexible for everyone. And we like RStudio because we can write reports, we can share our code, we can share our analysis all in one place. We can do our exploratory data analysis, and RStudio is really, really good for that. It's really good for the front end, and it's really good for the back end for making plots of our beautiful models that we get back out. But R and RStudio themselves aren't particularly good at running the big, deep models that we'd like to run, or accessing array jobs, because we've got 4 different models to run, 30 different data sets, and we're using 10-fold cross-validation. And so we're trying to run 3,000 odd models. And we couldn't put it in a for loop and run that, because, as Callum pointed out, we'll get chucked off the environment. But it is really handy. We can do our exploratory data analysis. We can set up, bring things in, bring in the Penguins data set, because it's a nice, handy one. With RStudio now, we can bring in all the different modules that NESI have operational. I currently have R4.2 loaded, but I could have had R4.1. I can bring back R3.6 because some people do use R3.6 because old packages won't work with current formats. And that comes under the module, the NESI module system, which then has all the system libraries that are associated with particular modules. Say for geospatial, there'll be particular system libraries that are needed. We can do our nice exploratory data analysis. It's great. We can print out a table. We can make a plot. But then it comes round to building a model, and RStudio in an HPC environment isn't great for actually doing all our in-depth modeling. So we're going to want to go over to an R script and set up a model, some kind of model. I've done a really simplistic one here. We're going to predict, see if we can predict our penguins species. I mean, I do all my model development here in line. Same thing, Control and R, run my lines of code, set a seed. But really I want to save it as a script to then make good use of the resources. Because when I come in with Jupyter, I've only got 2 CPUs and 4 gigs of RAM. Or I might be allowed to have 4 CPUs and 8 gigs of RAM or 120 gigs. But what I really want is I want 16, 32, and I want 64 CPUs, and I want full access to an A100 to run some kind of machine learning model for image analysis and things. And we can't do that. And so we need to talk to our users and help them and not be so intimidating about using an HPC and have them run a job. So we've got our R script. Our users will be used to an R script, and all we need to do is get them to convert over to a Slurm array job, or a Slurm job, a shebang, a batch script, and really simple, and keep it really clean and simple for them, and go R script, run my code, and I can do it all from within RStudio. I can set up my batch script here, and I can jump over to the terminal and run my penguins.r. Hang on, I'll scroll up to stop me mistakes. Oh, sorry, my job. Sorry, not the penguins.r. The classic mistake, typing the wrong thing. So run my job script, and it'll run away and go SQUE --me, have a look and see what's happening. Cool, it is pending. My job is pending. I've got my Jupyter job running. No problems. Hopefully this is a small job. Hopefully it'll run super quick. Yes, it's completing. I've got my navigation within RStudio. I can look at my directory structure. I've run this previously. I've got Callum was talking about the standard error, standard outs. I've got all that. I can navigate around in the terminal or look at all the NESI modules. So all within RStudio. And then I can go back to my Markdown document and then carry on, bring back in my model and load my model, do some predictions or do something, and I can knit the whole thing and I can send it off to whoever is my current boss. I don't work for ESR, but let's say I work for ESR. I'm going to send it off to Richard Dean. Richard wanted me to upskill in something in data science. And I can go and send it off and we're all done. Good. And I've made use of all the CPUs, all the RAM, etc. I've got my code in one place. And I've just had the 1 minute roundup and we're done.
Thank you so much, Matt. Yeah, and we're done with all the presentations for this session, but if you have any questions, especially for Matt, please do feel free to use the live Q&A button to do so.
I'm just looking at Russell Smithy's comment. I used to work
Yeah.
with Russell. I used to work with Russell at AgResearch. Russell was very, very good at getting around all the restrictions and permissions. So yes, this is the same thing. Like how do you make the most out of your NESI allocations and your NESI resources? Ask. Send an email to support@NESI. And
Yeah.
you'll get Callum. Callum will help you with your array jobs. Get a consult, and you'll get Alex Pletzer or Maxime Rio to make the most. I'll help you with your R, because we can use R. We can call in the Slurm array task ID into our R scripts and things as well.
We have one quick question, Matt, from Roland. How easy is it to reproduce on another HPC?
How easy is this? How easy is RStudio to reproduce on another HPC? I don't know. So every HPC environment is different. We saw there was a couple of other comments about Pawsey have got some workflows and things. Pawsey have their RStudio set up a little bit differently to the way we have. How long's a piece of string? If a particular work, I think how the workflow. Richard, Roland, are you talking about an RStudio style workflow and then applying it over to Slurm? Very reproducible. Write a script, run it in a batch job. It appears on the surface to be a learning curve, but once you're there, it's straightforward.
Awesome.
Yeah, so
Thank you so much, Matt.
yeah.
Matt, were you done
Yeah.
with answers? Sorry, did I cut you? No. Okay. We're good. Okay. If you have any additional comments, please feel free to directly message any of the speakers. And right now we'll have a very short tea break. We'll come back at 3:15. And the next session on engaging communities will begin from 3:15. So see you all then. Thank you so much for your time.